All right, welcome. So we've come a long way in the hands-on machine learning book. We did the entire part one, talked about all the foundations. If you guys recall, there's different algorithms, but one of our big themes that we talk about every week is how do you address overfitting? So it's not highly emphasized in this chapter, but I do want to make a point when we talk a little bit about image augmentations to reinforce that this is a super important part of computer vision. So today, I'm hoping that people are either somewhat familiar with CNNs or have read the chapter. So I will cover the topics, but hopefully try to use our time together to dig a little bit deeper into talking about why do they work, not just, what are they? And then for giggles, I actually prepared an interactive demonstration for you guys because I wanted to start testing my vibe coding abilities. So, um, so we'll mess with that. All right. So what is this chapter about? So we're now in the deep learning section. We went through the basics of how you actually build things with Keras and if you need to customize stuff. So with some of that coding stuff behind us, we're going to talk about these very specific building blocks, convolutional layers and pooling layers. And then we'll see examples of very famous CNNs. There's obviously instructions on how you can code this stuff. You don't have to do all this from scratch. And of course, these days, most of the time you go to Hugging Face, you download a model, you don't actually build things from scratch. And it talks a little bit about some classic computer vision tasks. So classifying, is this a dog or a cat? Object detection, tracking, semantic segmentation. So those are the topics we're going to go through. If you guys have any questions from reading the chapter, something that wasn't clear, or just questions in general, as always, at any time, feel free to post in the chat, raise your hand. And that's what we're here for, is to discuss and go a little bit deeper. All right. So the book, it starts by saying, hey, so there's this history when people were studying. So these guys, Hubel and Wiesel, did these experiments, and they saw that, hey, there's neurons that don't respond to everything you're seeing, but they just respond to stuff in a small portion of your visual field. And it looks like we might have a neuron that only responds to vertical lines in the lower left corner of your visual field, and another one that responds to horizontal lines in that same spot, and then something else that only responds in the upper left corner, and so forth. And so that's a little bit of the inspiration. And so we have our artificial neural networks, and up till now, we've mostly just been talking about fully connected layers. So if you have 100 inputs and you have 20 outputs, then basically you're going to have 100 times 20 different connections because every input is going to be connected to every output. All right. What we're going to do ultimately in these convolutional layers is we're going to have far fewer connections. So if you imagine an image coming in, height by width, let's just say it's a grayscale image. No, we're not going to deal with color yet. Okay. So we just have height by width and we have some pixel intensities. And then we can imagine that every pixel is an input. Okay. And we're going to output a similar looking object. It's going to be a picture that has height and width. We tend to call these feature maps. Okay. Because they're no longer raw images. They have some other semantic meaning. That's the features. So then if you imagine a pixel in our output, in our feature map, we're going to say corresponds to a neuron. All right. So when we build these convolutional layers, unlike a fully connected, instead of it being connected to every possible input, it's only connected to a subset of them. And here in this diagram, it's a little bit hard to see, but if you look closely, you'll see that the red, the blue, the purple, each of them is looking at exactly 9 pixels in the image below. They're looking at a 3x3 grid of pixels. Okay. That's a lot less than your whole image. You might ask, what do you do around the edges? And so one thing you can do is you can say, I'm going to keep my 3x3 inside the, I don't know what you want to call it, the frame of my input image picture. In which case, if you do that, then if you keep repeating this process, it'll keep getting smaller and smaller because uh, I don't know how to say it. I hope that's intuitive. It's going to keep getting smaller because you're at the boundary. You're constantly moving in a little bit. The other thing that people do is say, well, I can actually pad it. So if I have imaginary zeros around the outside of my image, then I can center my 3x3 anywhere, including on the actual far edges and corners of my input image. I This is not a hard rule, but I would say like I tend to see padded convolutions more often than not, just because it is a little bit easier to deal with the math. And since we're talking about GPUs and things, if you start with an image that's like a nice multiple of 32, 64 pixels each way, if you don't do the padding, then you start getting these numbers that are no longer nice round multiples of powers of 2, and then that actually can degrade your GPU performance. So sometimes it's actually faster to have extra zeros and just keep things really aligned to nice blocks of 16, 32, 64, stuff like that. I don't know if you guys have any questions about, I'll show the demo in just a second. But this idea of you have a very narrow receptive field, very common these days is just a small 3x3. So we talked about padding. Stride comes up occasionally. Most often you will just see a stride of 1, which means you just move this 3x3 one at a time. And the key concept here is in our output, every neuron, as it were, might be looking at 9 input pixels. But in a convolutional layer, every one looks at exactly the same number, say the same 3x3, and they use the same weights. So the upper left corner might have a weight of 2, the upper right corner might have a weight of -1, and every single output is using 2 in the upper left corner and -1 in the upper right corner. So this tying of the weights or sharing of the weights is the key phenomenon in terms of what we're doing here. Okay. So when every single neuron in your output is using the same filter weights, the same weights, then that's when you can think of this as a image filter where it's producing a certain sorry. Having trouble coming up with the right words today. But if like you've used Photoshop filters, one is like Gaussian blur, where it just basically blurs a little bit from the neighboring pixels. Okay. You can implement that by using one of these filters. For Gaussian blur, typically they use ones a little bigger than 3x3, so maybe 5x5 or 7x7. But basically, if you have a 1 in the center of your filter and zeros all around, that's the identity mapping. It's not going to change anything. So in a Gaussian blur, you can imagine that maybe you have 0.8 in the middle and you have a bunch of 0.02s around it. And so then just a little bit of every neighboring pixel is going to get smudged into your current pixel. And that's a Gaussian blur. All right. So that's the gist of this. And again, I think some people may have CNNs before. In the past, when I've talked about CNNs, I'm like, oh, let me find a really good page that has a good picture or a nice animated GIF that shows how you can use these same 3 weights and kind of move them around over the input image. But I've always found it a little bit challenging because if I have a static image, then it doesn't really show the moving around. And if I find an animated GIF, then I can't pause it when I want to pause it and talk about something. So I decided, okay, I'm going to vibe code and I'm just going to build something so that I can do the best of both worlds. And so let me copy this link for the people online. Paste this in the chat. If you guys want, you can download this onto your computer. It's just a single HTML page, self-contained. You don't need any libraries or installs or anything like that. And if we jump over to this demo, oh, actually, I don't want to do that because then I have to download it. So hold on, too many menus. My Zoom menu, go away. All right, let me see if I can Do I already have this open? This one. No, I don't have it open in this window either. Oh, wait, here. All right, so I have a demonstration for you here where move this out of the way. On the left, we have an input image, and you can see the image. This is grayscale. It's not color yet. You can see the image, and then here are all the numbers that actually correspond to that input, and their intensities between 0 and 1. Okay. And I have a filter. I apologize. The font is really tiny. You're going to have trouble seeing it. But what it has is -1s on the left column and the right column, and 2s in the middle. Okay. And what this does is this is a vertical line detector. Okay. And so what it'll do is it'll have high values. You'll see white where it finds vertical lines, and then you'll see darker where it doesn't see vertical lines. And so what we see here is a very strong white stripe corresponding to the white vertical line here. And we see some middling values for the diagonal line because it's not vertical and it's not exactly vertical. And then you'll notice that this strong horizontal line here just gets completely erased by this particular feature. So it's really down-weighted any horizontal lines, and it's up-weighted vertical lines. And so in this demonstration here, what I can do is I can click on any particular cell. And so this is without padding. So the upper left corner, hopefully you can see it here, this green pixel is formed by a combination of these 3 by 3, these 9 pixels in the input. And what we're going to do is we're going to take the values for these 9 pixels, we're going to multiply it by our fixed set of inputs, so our -1s and 2s and -1s. And then we're going to sum up all of those 9 values, and we'll get a final result. And so what a CNN is going to do is it's going to do this over and over again. So at this position, it's going to take these 9 pixels as inputs in the upper left corner. And then when we move one over, it's going to take the next set of 9 and the next set of 9 and the next set of 9 and the next set of 9. And then eventually we get all the way to the right. And then what we do is we move down to the next row, right? And we do this same thing. And so if you download this file and you play with it, you can actually see the numbers. FYI, I vibe coded this in an hour. I didn't actually verify the number. The calculations look like they're right. But the important concept was just to show which input pixels are being used in order to calculate each individual output in our feature map. Okay. And so if we want to look at it in an animated sense, I can just try to kind of click quickly and get the sense for it moving across. But if we wanted to pause it, now we can pause it. We can take a look at the actual numbers and confirm that they multiply and they add up correctly. All right. Now, as a quick demonstration, this is got -1s on the left, 2s in the middle, -1s on the right. If I wanted to make this into horizontal detector, I can just do -1s on the top and bottom and 2s in the middle. And so what I can do is I can quickly change this. And now I've got a horizontal line detector. And what you see is, in fact, this horizontal part of the 4 lights up very brightly. Again, we get some intermediate stuff on the diagonal. And now, not completely, but a lot of the vertical part of our input has been deactivated. All right. And then I can actually do 2s on the diagonal if I want to detect diagonal lines, right? And so now you see the slanty part of the 4 is actually lighting up strongly here. And much of the horizontal and vertical lines are now de-emphasized. So the point of this is that people played around with these kinds of filters as feature extractors, but now we're doing deep learning. You don't have to pick these. I mean, I hand pick these because these are some numbers people know kind of do these things, but you don't do this. We randomly initialize the filters, and then we use gradient descent, just like we've been talking about for training, and the model will learn which filters are useful for various things. And the um, the information, oh God, I'm now blanking on all my terminology today. I didn't get enough. I had to go early to drop my daughter off at the airport this morning. I think I didn't get enough sleep. Um, but at the end of the day, what's happening here with these small receptive fields is that each filter is only looking at a small region. And then what we're going to do is, we haven't actually talked about this, we're going to stack layers, and the layers can compose different features that it sees in a lower layer. So if you wanted to look for a square, then you might actually look for two vertical lines, two horizontal lines in the right places. And then voila, Bob's your uncle. You have a square detector. Okay. Now, obviously, some things are a little bit trickier. What's the definition of a hand? How do you detect a hand? Okay. And that's the beauty of this, is that for years people were trying to come up with manual ways to compose things to say this is a good way. But we just let the computer do this. And as with deep learning in general, to learn good patterns requires a lot of data. And so that's one of the reasons why, even if somebody had the bright idea, and I believe there were people who proposed things like CNNs earlier, they would not have had the compute and they would not have had the data in order to actually test out their idea. So a lot of the ideas in machine learning we'll see have roots in things that people proposed in the 50s or whenever, and there just wasn't the ability to test them out. Yes. Yeah. So the question is, what distinction, what makes this stuff work now that it didn't work in the 50s? And the number one answer is really it's just computing power. So, uh, yeah. So we're talking about multiple orders of magnitude. So probably the computing we have today is, I don't know, I'm going to guess 5 orders of magnitude, so 100,000 times faster than the computing available in the 50s. And so you can imagine if, like, somebody complains today, like, oh, I'm doing this Kaggle competition and it took me a day to train my model. Multiply that by 100,000. I don't know what 100,000 days is, but it's like many, many years. And so that's why nobody would be able to do things like this. And then obviously we stand on the shoulders of others, and so there's other things. You know, people use sigmoid activation functions early on for biological parallels, and then ultimately we realized sigmoid is actually kind of a bad activation function because its gradients are close to zero pretty much everywhere except right in the dead center. And so it has a very narrow region where it's good at learning. And then as we kept scaling up, we found that switching from sigmoid to ReLU wasn't even enough, and we needed other tricks. And that's why these LLMs you'll see have zillions and zillions of normalization layers. And it's all about trying to keep the model in a happy region where it's actually learning and you don't have these dead neurons. Yeah. Yes. Yeah. So the question is, as we do this, we're sort of losing the outer edge of pixels. You can sort of see this white stripe around the outside represents the pixel we lost as it shrank from the input is 20 by 20 and the output's only 18 by 18. So it shrunk. Okay. And so that's why we use padding. Okay. And so if you just throw extra zeros around the outside of the input, then you can wind up with a 20 by 20 that's the same size as the input. And that's more the norm. So directly to the point of your question, that's more the norm because you don't have this shrinking phenomenon. It makes the math easier. It's not a completely free lunch because sometimes the behavior at the edges is a little bit different than the behavior in the middle. So if you're in the corner, you're only getting 4 inputs and you're using 5 zeros. And so that might tend to give you a weaker signal than in the middle where you have 9 inputs, 9 real inputs. Okay. And you can do other things. People do other kinds of padding. I'm not going to get into it in order to try to avoid some of those problems, but it is, yeah, it's not just like this Zoom panacea. There's only one way that everybody does padding. So you could try and use an average value instead of zeros, like, 127s on the 255 point scale. That has some minuses. So then some people say use actual pixels from your image instead of just using some arbitrary thing. So there's a few different techniques. So if you guys don't have a good intuition around on how convolutions work, hopefully you can play around with this, and this little demo will give you a solid understanding. All right, now what we need to go to next is, this was assuming a grayscale input, but what do you do if you have an actual color image and it's got 3 channels, R, G, and B? Okay, so then what happens is our filter is no longer just 9 weights. It's not just 3 by 3. It's 3 by 3 for every single input channel. So for a 3 color input, you would then have, well, by coincidence, they're all 3s, but you would have 3 by 3 times 3, you'd have 27 weights. If we had a 5 by 5 filter, we don't have 25 weights, we'd have 75 because we have to have 1 copy for red, 1 5 by 5 for green, 1 5 by 5 for blue. That was something that I didn't really understand very well when I first started hearing about CNNs. All right. Now, how do I get back to the tab with my notes? Sorry, guys. So all these pop-up menus. So hopefully this diagram helps a little bit in terms of understanding. So when we have a filter, if you kind of look here, it's not just pulling from a one-dimensional 3 by 3, but it's actually pulling from this 3-dimensional box, this sort of cube shaped. Okay. And we can have more than one of these CNN filters. So what this shows here is, right, you've got like about a dozen of these filters. And so each one of them can be looking for a different thing. We can have a vertical line detector. We can have a horizontal line detector. We can have things that look for certain colors, whatnot. Okay. And then the number of outputs that we have, the number of filters we have in a certain layer, is the number of inputs for the next layer. And one of the things that is very typical is, as we go deeper into our model, we're going to increase the number of outputs. We're going to increase the number of channels. So when you're working in code, the image usually comes in as a 4-dimensional tensor. So we know we have height and width on an image, and we have the number of channels, which starts at 3. We're going to grow the number of channels. But then also we have the option to process a batch of images. So we could process more than one. And so that's why we have this 4D tensor. And the book notes that the convolution that we're talking about is a 2D convolution. And it's called 2D because we think of images as 2D, but just know that the dimensionality of your input tensor is going to be 4D if you're using a 2D tensor, which sometimes seems a bit a little bit not intuitive. Okay. Um, there are some other details. So as with fully connected layers, we usually have a nonlinearity. We have an activation function that we stick in there. So you can imagine between adjacent convolution layers, instead of just having convolution next to convolution, we stick a ReLU or something in between there. The other thing is that you have to initialize the values for these filter weights. And the good news is you can just basically use the PyTorch or the TensorFlow or the JAX default, but you can specify exactly how you want, what kind of distribution you want for your initial values. All right. Any other questions? I tried to cover it, but also like move a little bit quicker than maybe sometimes in the past when we talk about CNNs. All right. So the next section in the book talks about memory requirements, and I find this a little bit funny because when all we had was CNNs as the thing working really well in deep learning, people were like, "Oh my God, I'm running out of memory because these CNNs are so big." And then the book's talking about like, um, this layer requires 12 megabytes to store the weights on the GPU, and like now we're talking about LLMs with 1 trillion parameters. So 5 orders of magnitude bigger than this one layer. And this is not a whole model, it's just one layer. But still, so the reality is, as much as they may be kind of big, by today's standards, they're not big at all. I see a hand raised. So yeah, go ahead.
Can you hear me?
Yes.
Thanks. I have a question about receptive fields,
Mm-hmm.
because once we go and stack more layers, then at the end we'll have a receptive field that spans across the whole input image and or input pixels. And I'm wondering how important this is. Like, do we in real life calculate, the number of layers just to get to that point that, yeah, the output layer can span across all input pixels, or we shouldn't really care that much and just go and experiment and see if that works for us.
Yeah, that's a great question. So if we start with a 3x3 filter, then in our first layer of our model, the most anything can tell is what's happening locally in this 9 pixel square region. Okay. So there's no way you could even roughly approximate, is this a picture of a dog or a picture of a cat? It's just impossible. It's too local. So if you have 2 3x3s and you then have them input in the next layer to something, then even if those 3x3s overlap, you're still going to get a larger area. So let's say a 3x4 area that you can see. Okay. If you take 9 3x3s and you connect them all together, then you're going to end up with a 5x5 region that has some influence on you. And so that's what the question has to do in terms of this growing receptive field. So, yes, if you wanted to classify the image, at a minimum, you would need enough layers in order for your receptive field to be the entire image. That's a minimum requirement. The reality is usually we're going deeper than that. So you don't have to actually worry about calculating, is my receptive field at least the size of the full image? Because usually we're 2, 3, 5, 8 times whatever that minimum is. And so it's not really the concern at that point. Did that answer your question?
Yeah, thanks that.
Okay, awesome. Any other questions? All right. So we've only covered this one concept. There's another key concept. So these convolution layers, if that's all you had, you could get by, but it would not be as efficient. We also have these pooling layers, and we can think about it very abstractly. But like the reality is, the most common thing you see is a 2x2 max pooling layer. All right, and basically what that means is, like CNNs, where you have a small region of input and you have one output, A 2x2 max pooling has a small region of input. It's just 4 pixels. And then what max pooling does is exactly what's in the name. It looks at, of those 4 values, which one is the maximum, and that's what it outputs. So a max pooling layer doesn't need weights because it's not multiplying or anything. It's just picking the biggest. All right. Typically what you do with a max pooling layer, and this is the default behavior, is a 2x2 max pooling layer would have a stride of 2, which means that there's no overlap. You're just jumping every 2 pixels. And that means that then your output size is going to be 1/2 the width and 1/2 the height of your original input. And that's on purpose. That's exactly the purpose that these pooling layers perform, is they shrink the size of your input. You can, as we've talked about, do convolutional layers without padding, and it will gradually, like 1 or 2 pixels at a time, get smaller. But the max pooling is obviously going to do it much faster if it's cutting it in half. And don't want to go like too much into details, but basically the idea is we don't need the level of compute that you get by having filters over the entire image. So a common thing would be, let's say you have 2, 3, 4 convolutional layers. And now we've got some higher level concepts. We understand textures. Do we see triangles or maybe something that looks like an eye or a nose or a finger or whatever, something like that. And so if you're thinking about maybe not quite that high level, but if you're thinking about a concept of like, do I see an eye shape, a circle? Do I see a dark patch, a light patch? You don't need that at the pixel level. You're now talking at a slightly higher granularity. In the lower left corner, do I see a dark patch? Maybe if you're detecting for like grass or blue sky, you would say, do I see a lot of green? I don't care about the exact shape of it, but do I see a lot of green at the bottom of my image? Do I see a lot of blue at the top of my image? And so you don't need that kind of decision at the pixel level. You can be a little bit more granular. And so that's where you can cut the dimensionality in half, and you can then say, okay, I'm still talking locally. I'm not talking about the whole image. Do I see blue in the upper left corner? And I don't have to be talking about on a pixel by pixel basis. Then we cut it in half again, and now I'm talking about a region in the upper left. And eventually, as we do this, we can get down to a fairly small granularity where your input image gets cut half, 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 until now you're talking about maybe something just like a 8x8 or 4x4 grid that's really sort of saying like, hey, I see something that looks like a head here, and I see something that's like a tail there, and the texture on these things is it's furry, and the color is it's, I don't know, whatever, brown and black. And then ultimately, when you compose all those things together, you're like, I think this is a German Shepherd. Okay. But the reason why we need to increase the number of channels is because it's not enough to just say in the upper left corner, I see blue. It's not enough to say here, I see a head shape, right? You still need to know what color is that head. Are we talking more of a dog head, a human head, a cat head? And so when I sort of colloquially say the model sort of sees a head in this portion of the image, it has to have a lot of options for what it sees in that region. And so that's why we don't just stay at 3 channels. If you built a CNN that had only 3 channels the whole way through, then that means that at any point when you're talking about the upper right corner, you can only say 3 things. What color is it? What texture is it? Do I see a one thing? All right. And so what is common is you will see the number of channels doubling, sort of at the same rate that the height and width are halving, and you will very typically see 512, let's say, channels, maybe 1,000 channels. All right. So there's a lot of different things, a lot of different features that that the CNN is learning. So the key thing about this particular design, the book doesn't really kind of get into this, although it definitely mentions it. It doesn't really like hammer the point. What CNNs are taking advantage of is a particular inductive bias. Okay. The inductive bias is that at any granularity, things that are close to you are more important than things that are far away from you. So at the pixel level, what matters the most are the pixels that are immediately next to you. Okay. If you're talking about texture, what matters most is texture of nearby regions, not far regions. So if you're talking about a dog and you're somewhere on the body, it's very important that your fur be the same color as the fur near you or the same texture as the fur near you, except obviously like a dog with spots, right? But that's far more important to you than the color or texture of some region in the upper right corner of the image, because maybe that's sky and it's no longer part of the dog. Okay. So at every granularity, whether you're talking about low granularity or high granularity, it's always the case that the things near you are more important than things far away. And that's why having these different layers with very small filters, 3x3 filters, why they're able to learn. If you had some kind of input that did not follow this particular pattern, I don't know if I can think of a good counter example of a kaleidoscope image or whatever, right? Kaleidoscopes have like this six-way symmetry. Maybe CNNs wouldn't be the perfect thing for a kaleidoscope, because if you were testing like, is this or is this not a kaleidoscope image? What you really want to know is, if I'm looking here at my other six, symmetry points, do I see the same color and the same shape? And CNN might not have quite the right bias for that. So it might be a little bit slow to learn that. And I don't even know how I would build a six-way symmetry detector, but if you could build something that specifically looked for that, you might actually find that it learns faster and has higher accuracy than our vanilla CNNs. So that's a key thing, is they're using this particular inductive bias. And one of the messages that I kind of want to circle back to if we have time at the end is this tension between Rich Sutton's, bitter lesson is that if you can have large volumes of data and large volumes of compute, in the end, the system that doesn't have a lot of handcrafted rules and inductive biases can ultimately learn general rules that outperform anything that you can think up. And that's what we've actually seen in computer vision now, where the transformer models that don't have this locality inductive bias of the CNN filters, they're able to eke out better performance than CNNs. But this inductive bias is really, really good. So they're not totally trashing CNNs, but they're able to slightly do better than them. Doesn't necessarily mean you want a transformer for your use case, because it's a lot more compute intensive, and on average they're trained on way, way, way more data than a CNN in order to get to the same performance. Okay. But that is something to understand when we talk about these building blocks, is what sort of bias are we putting into it? And more general is better if you have billion, 10 billion, trillion level scale data. So, AlphaFold gets the Nobel Prize. You cannot train AlphaFold until you have that like 100 million scale number of input examples. So you have to solve that problem, or it doesn't matter if you have the perfect architecture. So sometimes when you look at a hard problem, the problem isn't that nobody can think up of a good neural network to try to model that. The problem is we don't have enough data, right? So we could solve Alzheimer's if we had the perfect data set, but we don't even have the data. And then we need to potentially map, millions of spots on your genes, and there's epigenetics of what's activated, what's not. So it's a very large problem, and also we don't have data. All right, so implementing is relatively easy. In Keras, you can have like basically one line. So here's the the line for max pooling. Yeah, I see a hand raised online. Go ahead.
Thanks for explaining about the channel, importance of the channel. I guess I have an intuition question that why can you do you have an intuition like why we when we apply the filter why the pixel size shrink but the channel size grow? So what's the intuition behind this?
Yeah, so what we are trying to do is go from global to more global understanding of what's in the picture. But when you go from fine grained to higher grained, there are more concepts that you might want to encode. So let's just say we were just doing pictures of faces. Okay. At the local level, you may only have when you're at the pixel level, you start with like vertical lines, horizontal lines, curves, whatever. When you get to slightly higher than that, you may just sort of be saying like, do I see a certain shape here? Circles, whatever. What color am I? But if you imagine as you get more global, then not only are you saying sort of like, is this an ear, but like, what is the skin tone? Right? I see hairs. Are they straight or are they curly? And ultimately, as you get far enough out, you want the two ears to match each other reasonably. Okay. Um, uh, People could have a particular hairstyle, but otherwise, you expect a certain uniformity of the hair color. There'll be highlights, there'll be this, there'll be that. But so the number of concepts that you need to encode, say, 1/4 of a face is just way, way, way more concepts than you need to encode a small, let's say, 1 centimeter square patch. Then you just need to know, is it a flat region? Is it part of the eye? That's going to be very different, right? You have the iris and the white of the eye and whatever. But if it's just somewhere else, then it's mostly skin tone. If it's near the eyebrow, right? So does that make sense what I'm saying in terms of the more global you go, the more concepts you have that you're trying to understand and represent?
Yeah, that makes sense to me. You're basically saying the channels that like put in the information of a coding, right? Encoding everything there, so you keep the information. But the pixel you just like shrink because you go global and global. So it's like a high level. So in terms of high level, the concept is less, but it store information in the vertical line, which is the third dimension. Uh,
Yep.
the,
Yep.
yeah. Okay. Cool. Thanks.
Yeah. Another quick note is that uh I don't know that I've seen this written in textbooks. But as we build these feature maps, okay, we do the max pooling, so they tend to get smaller and smaller. So if we started at 256 by 256, halfway through the CNN, maybe we're down to 128. Let's say 64 by 64. Okay, but the number of channels has grown. So maybe at this point we have 32 channels or something like that. The 32 by 32 part of it, the height and the width part of it, is actually corresponding physically to the regions that you would think that intuitively they would correspond to. So the upper left in our 32 by 32 corresponds to the group of however many pixels in the upper left corner. The center of the 32 by 32 corresponds to the center of our original image. So these intermediate feature maps are all, I don't know how to say, but geographically, they still correspond. So if you were looking at an image that had a dog and it had grass at the bottom, where is the fact that there is grass in the image encoded will be the bottom of every feature. Where is the sky information encoded? Does the sky all blue? Does it have clouds in it? You would not find that in the middle of your feature map. It's going to be in the exact same region that your actual sky pixels were. Okay. So this is again this I don't know if I want to say inductive bias, but this is sort of the geometry of CNNs. So where do I have it? I had a question here. So a fully connected layer is a superset of the weights and connections in a CNN. The CNN actually is massively fewer. So if you have a 256 by 256 image, every neuron in the output can have 256 squared connections, but in a CNN, it can only have 9. Okay, so it's massively less. So there are two really strong reasons why CNNs are preferred over fully connected networks. So hopefully we've kind of teased that out, but I thought we should like be super clear and actually address that here. So anybody want to take a shot at one of the two reasons why CNNs specifically are better than fully connected for something like images? Yeah. Yeah. So the spatial aspect, CNNs actually learn faster even though they have fewer weights. It's because if you want a vertical line detector in the upper left corner, it's probably a good idea to have a vertical line detector everywhere in the image. And so by sharing the weights, if you wanted to get the exact same functionality out of a fully connected layer, it would have to learn all thousands of copies of those weights over and over again for every location in the image. Yeah. Jerry, you have your hand raised? Did you have a different answer?
Sorry, I think it's a mistake. So
Oh, that's for okay. All right. And so then the other reason is just that size-wise, obviously, having 9 weights to learn instead of having 10,000, 100,000 weights to learn, it's just a lot faster, a lot less compute. So those are the two main reasons. But it's not just about the compute. Even if you said Ted's going to run a CNN on his laptop with no GPU, I'm just going to run it on CPU, and you get to use the Meta 100,000 GPU cluster and you're going to run a fully connected one, mine still might learn faster than yours, just because it's great to have all of those weights, but it's also a lot of directions you need to wander around in order to learn the signal. So my guess would be it's possible that even if you had all of that compute at your disposal, the model might just wander around and might never actually converge on a good model with, say, like 95 accuracy. Whereas the CNN, it might be slow on your little dinky CPU, but it will learn, and you will very quickly get to 50% accuracy, and it'll just keep creeping up, and it might just be slow on a CPU, but you'll get there. Okay, so then the next thing the book does is it talks about a bunch of different architectures. I'm just going to highlight a couple trends and a couple specific components that we see in them. So typically what you see is you see a few convolutions and their activations and then a pooling layer. So it's not 50 convolutions then a pooling layer, and it's not one convolution pooling. It's usually like 2, 3-ish convolutions, maybe 4, and then a pooling layer. Okay. So it gives it the ability, like I said, if we're just detecting vertical lines, that's good, but that's not like a kind of a whole lot. You're better off sort of saying like, I'm composing some of those things into a square, a circle, a triangle, and then I can take that concept and save that off and then reduce my dimensionality and then say, okay, if I'm composing these triangles and other things, then get those concepts and then shrink it by a factor of 2. Over time, what we see is that the models get deeper. So these early models, you're like, wow, it only has like, 12 layers or something like that. And then a couple of years later, you're going to see it has like 20 layers. And then eventually they hit the wall where they were having trouble training these models as they got bigger. And so that's where we see ResNet comes in 20, I'm trying to remember, 16, something like that. And these skip connections or the residual connections were a major breakthrough. People didn't necessarily know this, but in hindsight, we can say this was a massive, massive, major breakthrough. If you do the math, what you can see is that the gradients, when you do back propagation, when you have a bunch of layers, then you have the partial derivatives that you calculate, and so you basically get the partial derivative with respect to your loss at the top, and then you get multiplied by the partial derivative of things in the last layer, multiplied by the partial derivative of things in your second to last layer, and so on and so forth. And if all of these numbers are less than 1, okay, by the time you go past 20 layers, multiplying by 0.1 every time, you've now reduced your original gradient by a factor of 10 to the 20. Okay. When you have a residual connection and you're summing them, then what your gradient is the gradient of that plus the gradient from the particular layer. Okay. And so it doesn't matter if you have some partial derivative that shrunk by a factor of 10 to the 20th, you still have this other component that is completely unaffected by how many layers you go down. And so you will have a non-zero gradient throughout your ResNet. And so what happens without residual connections is the last layer is the first one to learn. Okay. And then you get weaker and weaker signals the further you get in a deep model. With a residual connection, it's possible to have all the layers sort of learning at roughly the same speed. Another thing that later research has uncovered is that when you look at the loss function, it turns out that small changes when you have layers chained in a row, it's like this domino effect. One small change in an early layer, 4 layers later, can cause a fairly large change in your output and a large change in your loss. So you get this highly variable loss surface. And so this is a particular visualization of the, I don't remember if it was classification problem or not. Let's just say it was binary classification. So dog versus cat, the error you get predicting dogs versus cats, if you tweak the parameters a little bit, it's this highly variable, high variance, very dramatic looking landscape, worse than most mountain ranges that we have in the Sierras here in California. With the residual connection, when they mapped it on a similar scale, it's this image on the right, where it's just like, you can see sort of these corners. It's like not clear exactly where you go, but once you get anywhere in this large region, it's just straight down to find the optimal loss at the bottom of that well. Okay. So residual connection, super important, and we would not be able to build models more than about 20-ish layers deep if it were not for residual connections. Yeah, do you have a question? So I'm not showing too many diagrams. You can refer back to the book. I can look for, but basically the idea is up until the ResNet came out, all of this business, when we talk about multiple layers, they're just stacked like dominoes where the input to one layer affects the next layer directly and only the next layer directly. Everything else is indirect as a consequence of that. And so you can imagine that if you push that up by 0.1 and then it pushes up the next layer by 0.2 and that pushes the layer after it up by 0.4, it doesn't take too long before things can actually become dramatically different. All right. And it turns out that these skip connections, what the diagram is actually showing is that if originally you were modeling some particular pattern that they just call h of x, all right, now that you have this direct route where the value x gets sent directly to the end, in order to get the exact same results, you just need to learn the function h of x minus x. If your model was smart enough to be able to learn some weird pattern h of x, it's probably able to learn the pattern h of x minus x. So worst case scenario, it can get the same performance as the non-residual model. But what we've learned is that actually the ease with which it can find the path to a really good answer is much, much, much easier. I don't know if that answered your question. Sorry. Yeah. Okay. Thanks. And so today, as far as I know, I can't think of any exceptions, but there's probably something somewhere. But basically, every model that you can think of, every LLM, AlphaFold, they all use residual connections. I cannot think of a single model that does not. A couple interesting things they mentioned. One they mentioned is one-by-one convolutions. So when I first have one-by-one convolutions, I thought, well, that's kind of dumb because you can only learn from one pixel. How much can you learn from one pixel? But I was forgetting that one pixel actually has many channels. Okay. So if you have 256 channels, then you still basically are doing linear regression on 256 inputs, even though it's a one-by-one. So the way we talk about this now is that a one-by-one convolution is mixing information in the depth direction. A regular 3x3 filter is mixing information in the spatial directions, height and width. And it actually is mixing things in both the spatial and the depth directions, which gets us to the next bullet is somebody came up with, oh, I could actually build a modified CNN that only learns in the spatial direction. It doesn't do spatial in depth at the same time. And I can do spatial sequentially and then do one-by-one depth only. And what they found was, let's say you got 95% the performance of a regular full 3x3 filter. But it turns out that the amount of compute you need to do spatial and then depth only is like 1/10. So you're getting 95% of the performance at 1/10 of the compute. So if you wanted, you just throw a few more layers in to make up for that 5% performance drop. And so these depth-wise separable convolutions are great for applications like, you know, edge device where you have limited compute. So it's a lot less compute and you're getting very similar results. So I promised we would talk about overfitting. And so every time we talk about machine learning, basically these days, we're talking about complex problems with lots of data. Early, you know, machine learning was smaller, simpler problems. And so you could talk about things like linear regression. But these days we're talking about large problems. And so overfitting is a problem when we have these large numbers of parameters. And so one thing I want to mention is dropout. So you see dropout very, very commonly in CNNs. And for that part, almost every other model too. But one of the big things, and I didn't bother copying it, but there's a box in the chapter that talks about image augmentations. So computer vision is actually one of the easier domains to attack because we have, for most use cases, many different augmentations that are considered valid. So if I'm doing classification of dogs versus cats, if I have an image of a dog and I flip it, I do the mirror image horizontally, it's still a dog. If I rotate it 2 degrees, if I rotate it 5 degrees, if I rotate it 90 degrees, it's still a dog. If I blur it a little bit, if I change the colors a little bit, if I lower the contrast, all of these things change the pixel values, which makes it harder for the model to overfit on a particular, you know, set of inputs. But it doesn't change the fact that it's a dog or change the fact that it's a cat. One of the reasons why LLMs took longer to come around, okay, not the only, but one of the reasons why they took longer than computer vision is because LLMs tend to overfit much more than computer vision models because there's not really any fully agreed upon safe ways to noise your input. So if I take the Gettysburg Address, 7 years ago, I don't remember it. Our nation was founded. How do you find a synonym for 7 to noise the 7? How can I rotate that sentence by 3 degrees? I can't mirror image it. I can't say, well, maybe you could like limited say 7 and 4 years, because that's still you could talk like Yoda and sort of reverse the word order, right? But nobody would say that that is fully preserving the meaning of the sentence, right? Somebody who talks like Yoda is not exactly identical to somebody who does not. And if you see the word big, they're like, oh, there's lots of synonyms for big, but in every single place, you can't replace the word big with large. Okay. So I have a sentence and I say big data. If you say large data, that's not big data, right? If I see the Big Dipper up in the sky, large dipper is not a thing. So one of the reasons, it's not the only reason, but one of the reasons why computer vision was able to take off is that you can have a training set of 10,000 images, but by augmenting it, you can essentially create millions. It's not quite the same thing as having a truly diverse set of 1 million images, but you can create virtually unlimited number of input images in order to fight overfitting. And in NLP, we really don't have that ability. So it's common when training a CNN that you run multiple epochs over your training set. It would not be unusual to see 100 epochs. It's not wrong if you do 1,000 epochs. It's not wrong if you do 100,000 epochs, as long as you're doing augmentations. In NLP, I think the average is something like 1.1 or 1.2 epochs. They don't reuse text at all because the model will just overfit. So that's something key to understanding ML and deep learning in general, and specifically this. And then the other thing I wanted to point to is that dropout seems very dramatic. And so if you had like a 40% dropout somewhere, when I first started doing deep learning, I kept lowering the dropouts because I thought this is crazy. This is far too drastic. But people do use those, and that is actually a sensible, people have experimented. Similarly, the augmentations that people do, at first they were talking about small ones, like slightly tweaking the contrast, doing a mirror image, doing a 5-degree rotation. Nowadays, what people have found is that you can do things like punch big black holes in 50 to 75% of your image and still ask, is it a dog? It's crazy. There's weird things that people do that I do not understand. The mix-up augmentation, where you take 2 different images and you blend them some percentage, and then you change your label to correspond. So you take a picture of a dog, you multiply it by 0.75. You take a picture of a cat, you multiply it by 0.25, and you sum up all the pixel values. So if you look at it, you're kind of like, yeah, I see sort of like a faded cat, and I see the regular dog. And the label for it, instead of 1 dog, 0 cat, is 0.75 dog, 0.25 cat. And this augmentation works amazing and is like caused behind a lot of the state-of-the-art computer vision models. And it makes no sense to me that this is the right way to teach a model to understand the difference between dogs and cats, because you're never going to actually give it a 3/4 dog, 1/4 cat image. You're only going to give it dogs and cats. Yet this is like, so anyway, so just, I don't want to go too much of a rant here, but don't be surprised that the augmentations are very extreme and very unusual. All right, so moving a little quicker just to kind of wrap up here. So they say, hey, as an example of implementing it, the sequential way of defining a model in Keras is really, really nice, but it only supports 1 input, 1 output. So when you have residual connections, you have 2 inputs in some places, you have 2 outputs in some places. And so you have to use the more complex, define of class, the full way of defining it. But The good news is most of the time you don't even have to define things because you're just going to download something from Hugging Face. And so we do transfer learning. So you can download a model that was trained to do, let's say, I don't know, ImageNet. So dogs and cats and some flowers and some different things. And what you want is you want something to work on X-rays, which is like completely, utterly different. But generally speaking, you will need less training data and you will get better results if you start with that pre-trained model than if you just start from scratch with a randomly initialized model. All right. And so then finally, yeah, question. Yeah, so the question is for transfer learning, would you add a new layer? Would you change the last layer? Generally speaking, you often just have no choice, but you have to change the prediction head, the last layer, because if I have an ImageNet model and its prediction head has 1,000 classes, and I'm just trying to predict breast cancer, no breast cancer on an X-ray, then I need a prediction head that's a binary classification head. Okay. To go a step further, even if you could, most of the time people actually make very minimal changes. So they literally just swap out the prediction head so it's the right shape. And if you had a model that happened to have the right number, so here's a pre-trained model with 100 classes, and I need to train a new model that's going to detect all the different products my company, makes, and there's exactly 100 of them, then you wouldn't change it. You would just take the pre-trained model and start showing it some images and fine tune it. So Ryan actually explained the pre-training model to me one time when I was sort of like, well, this thing is so completely different. Why are we even using a pre-trained model? And he said, well, think of it at when you're that far away, think of it as random weights, but that the pre-trained model, we know the random weights are at a very good scale for learning. So, so even if we're going to end up totally altering them, at least we know that they're sort of in the right learning zone in terms of their magnitude and stuff. And hopefully we do get to reuse some stuff, right? Like a vertical line detector is still a vertical line detector, whether you're doing X-rays or you're doing dogs and cats. All right. So we're just about the end of time. So in terms of tasks, we talk about classification. So that could just be binary dog versus cat. It mentions localization. So you can do regression, have 4 numbers, the center XY coordinates and the height and width of the object in there. And one thing I wanted to mention, I think we've said this before, but it says, hey, mean squared error is the loss function we use for these 4 numbers that we're regressing. Say, well, the actual x coordinate of the center is 100, but we predicted 80. And so we're going to have a loss based on that difference, 20. However, if you want to know, do I have a good model? Mean squared error is not a very intuitive way. And so what people usually use is IOU, which is sort of roughly speaking, the percentage that the bounding box it predicted overlaps with the correct answer. However, I did want to state that this is another one of those motifs that we see over and over again in ML, which is that your learning signal, your loss function, is often not the metric that you're using to evaluate it. The metric you're using to evaluate it should be more aligned with your business goal. And I've had plenty of situations where I can't even really have just only one metric. You can only have one loss function. Gradient descent requires that you narrow it down to just one thing. And that's where people do this. I find it to be kind of theoretically ugly, not very pretty, but where they just say, well, I have 4 different losses and I'm just going to have, random constants to say how much I relatively weight each of the 4 of them. And so it's just loss 1 plus alpha times loss 2 plus beta times loss 3. And they wiggle the alpha and the beta up and down a little bit and they say, okay, we're done. I always find that to be a little bit ugly. but you can only have one loss. You often do need to have multiple metrics. And ideally, sometimes this can't happen all at once. But if you have a final trained model, ultimately, if this is for a business application, you want to translate that into dollars. So if you say I have a churn prediction model and you go to your boss and say, I have certain precision and recall, he's like, what the heck does that mean? It's like, okay. What I'm saying is if we actually have people call, these people and they prevent them from churning, that'll save the company $10,000 every month. Oh, now I'm interested. So object detection is the classic computer vision problem where we want to classify and localize, but potentially multiple objects in an image. So there are standard training sets, standard benchmarks for it, Pascal and Coco. And if you're going to do that, an important thing to know is this idea of non-maximal suppression, NMS. And so this is I would call it a heuristic. It's not really a special algorithm or whatever, but it just removes duplicates. So if you said, I think I'm 50% sure I might see a person here, but 40% the person's slightly to the right, it's not going to say there's two people there. It's going to say those are both just not sure predictions of the same person. That's the idea. The book goes a little bit into fully convolutional networks with the idea that anytime you have the output from convolutions and you stick it in a fully connected layer, you are hard coding. There need to be exactly this many inputs. That's what a fully connected layer expects. Instead, they say if you actually treat it as a convolution, then you can have a variable input size, and with it, you'll get a variable output size, but you'll never get an error message. And so that's the general concept underlying things like the YOLO model. It also mentions this mean average precision metric for object detection, which is the primary metric you'll see reported if you look up models or if you look at it in your research papers. They describe what does that exactly mean. It always sounds a little bit confusing because the words mean and average kind of mean the same thing. So, but I'm not going to try to explain it. You can look it up. Yeah. It is the exact same concept. In this case, it's a little more straightforward because it's just talking about two rectangles. So the intersection of two rectangles is the region in the middle, which will also happen to be a rectangle. That's the intersection. And then the union won't be a specific shape, but it's the combination. But it is exactly the set theory concepts. And so if they're identical, then intersection over union is 100%. If they barely touch in one corner, then IOU can be extremely small. And if they don't intersect at all, then IOU is 0. They mention object tracking and deep sort. And then finally, semantic segmentation. So now instead of predicting a small number of objects or something like that, we're going to make a prediction for every pixel. All right. If you're doing stuff with computer vision, reading a paper, and you see this transposed convolutional layer, I found them to be confusing. But I did kind of like the book's explanation where they say, imagine that if you were trying to upsample 2 to 1, that you basically like insert one blank line between one blank row between every row and one blank column between every column. And then you do a CNN in order to sort of interpolate, average, guess what the blank values should actually be. It's not literally what it does, but that's a pretty good intuition for. So the idea is that everything we've been talking about with getting our feature maps to have smaller and smaller height and width gives us a concept, okay, this is a dog, but now we have difficulty localizing exactly where it is. We need some way to upsample. And so transpose convolutions, one thing. Another thing is skip connections. And You will often hear about UNets. Early diffusion models use this UNet architecture. If you look at this diagram, you can see exactly why they called it U, because I think the U shape is pretty obvious. And it's these skip connections that make it different from just generic upscaling, because the idea is, oh, there's information at this level of scale that I can pass on to here. So what's happening on the right-hand side of a UNet is it's combining the conceptual information with the original, more local information. So let's say you go boom, 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 and it says, oh, I see a dog head, and I see paws, and I see a tail. This is a golden retriever dog. Then when you're going on this side, it's basically saying, out of a golden retriever dog, your region has the head. Out of the golden retriever dog and the head, your subregion has the nose. Out of the nose, you are the left nostril, and then you can decide pixel by pixel exactly what you want to do with that information. So that's the general gist. All right, so to wrap things up, we've mostly been talking about 2D convolutions. I find that they're sort of the easiest to have an intuition about because we can actually draw pictures and look at them. Like I showed you the vertical line filter, the horizontal line filter. You can have a good intuition. There are 1D convolutions. There are 3D convolutions where instead of having an X-ray, if you have a CAT scan or an MRI, a 3D image. So then instead of 2D pixels, we have 3D voxels. You will see 1D convolutions in machine learning. They are a very efficient, fast, cheap thing that can find simple patterns very quickly. The other thing to note is that 3D convolutions are a lot more expensive than 2D convolutions. So whereas we say a CNN is actually much faster and cheaper than a transformer model, even though the transformer model might beat it by a couple percent, 3D convolutions are unfortunately crazy expensive. And this is one of the reasons why computer models for looking at MRIs really haven't taken off because it's just very expensive to train them. So, yeah, so hopefully that does a good job summarizing the information in the chapter, but then also giving you this idea about this inductive bias, okay? And we have this locality of image data bias that makes CNNs a really good fit for that. Ultimately, you can beat it by not strictly enforcing that using transformers, but it does get more expensive. So yeah, hand raised, Jacques.
Can you hear me?
Yes, we can.
Okay. So again, I read over this chapter, had a few questions, but I'll probably try to read over that again. You mentioned before that as opposed to transformers, CNNs are better for 2D images. For like videos, does the same thing apply, or do transformers work better for evaluating videos and being able to describe what's happening in the video?
Thanks, Jacques. That's actually a really cool question. So it would take a long time to give you a super complete answer. What I will say is that when you look at individual frames in a video, ultimately, because CNNs work well on images, the inductive bias is good, and you tend to, at much less compute, get a very good answer with a CNN than with a transformer. When we now talk about the temporal dimension, and you think about going from frame to frame, if you stack these frames, you can actually think of it as a 3D volume instead of a 2D image, okay? And this is where I already said 3D convolutions get super expensive. The information, I don't know what's the word I'm looking for. The information patterns in the time dimension are very, very different than the information patterns in the height and the width dimensions, okay? Height and width, you're sort of like, hey, I see this sort of round shape with these colors. It looks like an eye. Okay. I see this bigger thing and it's got whatever I think they're fingers. I think this is a hand. Okay. You don't have things like that in the time dimension. In the time dimension, mostly you have, if you have a high frame rate, is objects very slowly moving, to the right. So it turns out in terms of efficiency, you need a lot less information storage in the temporal direction. So one of the first things we saw is you process each frame individually with a CNN, and then we haven't talked about it yet, but you use some time-based thing like an LSTM to just string together the CNN outputs. Okay. You could do a 3D CNN, but people don't because it's like crazy expensive, and the information density in the time dimension is very low compared to the information density in the image is much, much higher. So if you had a magic wand and you had like infinite compute, I think you could just use a 3D CNN and it would work. But since we don't have infinite compute, it's much more efficient to treat the time dimension with a less powerful model than either a CNN or a full-fledged transformer. Yeah, Sakershine. Yeah, 3D images, yeah. Mm-hmm. Yep. Yeah, so if you have medical images like an MRI and it's in 3D, then unlike what I was saying a moment ago about the time dimension in a video has sort of low information density, now you actually still have high information density in sort of the Z axis direction. Okay. If you're looking for a tumor, then sort of the shape in the Z direction is very meaningful. Whereas if you're just thinking about like a movie and you have a person walking from left to right across the scene, if the camera at the moment is not moving, then all the buildings and scenery are completely stationary, and you just have this one, person that's like moving. So that's why for something like that, you tend to lower the compute in the time dimension. For your question, would you use different kinds of GPUs or something? CNNs, we haven't talked about it, but can be implemented extremely efficiently as matrix multiplies. It takes a little bit of work to think about, I showed clicking on the green cells and moving across or whatever, how you would vectorize that and do it as one giant set of matrix multiplies. It turns out that a 3D CNN uses the exact same tricks. And so you can just frame it as one ginormous matrix multiply. It's just that if you do the math, that your filter has however many weights and your volume has height by width by depth number of pixels, voxels. It works out that it's like, I don't know, about 3 orders of magnitude more multiplies, more flops in order to do the exact same thing with a 256 by 256 by 256 volume relative to just a 256 by image. It's the same, right? It's the same matrix multiplies. It's just bigger and a lot more of them. So, but you don't need any different architecture. So it's the characteristics in terms of it's going to be compute bound, not IO bound. It'll still be compute bound instead of IO bound. It'll just be 2 to 3 orders of magnitude more compute, and that's why it's unfortunately just a pain in the neck. But going back, did I answer your question? I know I didn't give you like a detailed specific answer, but because the temporal dimension in a movie tends to have less information, we don't use something like a 3D CNN. We tend to just use 2D CNNs and string them together using a weaker model. because there's not as much information in the temporal dimension. Yeah. Was there a follow-up or a second question?
Is that for me?
Yeah, yeah. I
Okay.
saw your hand raised.
So yeah, so what you just said, because there's not a lot of information in the temporal frame, because you showed a video of how a video game was made, but I didn't get a chance to fully see it and understand it. But I do know that NVIDIA is doing something with like frame generation. So if you're trying to, I guess, get more information from a image, and you're trying to like get information from it, could you use uh that's what I'm trying to figure out, like the difference between transform and CNN as far as video, as far as images, to be able to, so if we took a piece like in the book, they show images of a woman walking in the park with bikes and buildings and everything. If the woman part is cut out or half of her is cut out, and you're trying to generate the rest of that probability, the same thing as a dog or a cat or whatever, and you already have the base information, the base input, would you be able to generate the other half of the image just from that information? And to do that, would you use a CNN or a transformer? I don't know if I'm explaining my question the right way. If you
So
have a portion of, like you have the full image, but a portion of it is cut off, to generate a probability of what the next of that part that's cut off would be, would you use a CNN or a transformer?
all right. So the first part of the answer is that generative models, uh, generally speaking, differ significantly from discriminative models. So we've mostly talked about discriminative tasks like classifying or segmenting pixels. So we generally need different, I'll 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 say more powerful models for generative models. But having said that, the difference between CNN and transformer when it comes to anything like image related is a pretty close tie. So you see people trying both approaches even still today. I would say maybe now within the last year or so, the scale has tipped towards the transformer side because it's just easier to do one giant transformer model that looks a lot like an LLM and have certain inputs and certain losses, and just train it instead of having like a CNN and something else. And some of this has to do with, again, how do you deal with the time dimension? If you have a CNN hooked up to another model to handle the time dimension, you have two different architectures you're joining together. And like I said, if you had all the compute in the world, you could do a 3D CNN. What people can basically do is they can do the 3D version of the transformer, but give less attention, less focus, less compute to the time domain and more compute to the height width domain. But it there is no real strong answer to your question. So for example, if you look at the latest Gemini and it's an LLM and I can upload an image and ask it to do something or whatever, the way it processes that image, it might be a transformer, it might be a CNN. It's kind of a coin flip. Slightly more transformer these days, but it's not like a hands down terrible decision to use a CNN. And so if you see something that's like designed for an Android phone, it might tend to be a little bit more CNN common because it's easier to just do less computing with the CNN. If you're looking for a research paper that's trying to get a world record state of the art number, probably transformer these days. So I hope that answered your question.
Yes, it did. Now, but again, I'm thinking about how actual applications of this. So, for example, I'm trying to detect um, in an eye, like it's eye. I see an image of it, like I'm looking through an eye to do detection of diabetes. Like the what it's more comes down to the processing, but if part of it is not clear or visible when you have an image, when you take an image, would would a CNN or a transformer be able to clean up that part that's more blurry or it is blacked out or whatever? And what percentage of it would be right in a sense, because they're doing a prediction of the part of the image that is not exactly clear or blacked out once you take a snapshot. But
If I'm hearing your question right, if you have missing information, there's two separate tasks. There's filling in the missing information in a realistic way for some purpose. And then there's making predictions based on the full picture, including the missing information. Off the top of my head, I mean, obviously we can get really, really into the details, but at a high level, if you're using a model to fill in the missing information, you're probably no better off than if you just built a model that allows for information to be incomplete and it makes its predictions without complete information, because you're not really gaining any information. Anything you fill in the missing parts is based on the parts you could see. And so you could have your prediction just be directly off of only the parts you can see. Instead of having to explicitly output to the user what is the implied part, the part you can't see. Now that might be something you want for separate reasons, just so the user can kind of like see something. But at a high level, like if I said, go much simpler than computing, right? If I were predicting the price of houses and some of the listings were incomplete, they for whatever reason didn't have the information, what type of flooring is there, how tall are the ceilings, but other listings do have that information. I would just build a model that can accept nulls, NAs in some of those fields and try to make the best guess. It's not necessarily going to assume, just because it's blank, that the ceiling is a specific value. It might look at all the other things to say, well, for these kinds of houses with the other fields filled in, I think it might have a high ceiling. And for these, I think it might have a low ceiling. So I'm not talking about just good old fashioned, data imputation up front, right? The model can say, sometimes I'm going to guess this, sometimes I'm going to guess that. But it doesn't necessarily have to output what it guessed about the height of the ceilings in order to just predict the price of the house. So to me, those are two sort of separate problems. Do you want it to be able to predict the price of the house, even though sometimes it doesn't get this field, versus do you want to show the user some kind of best guess for what the missing things are? So that's sort of my high level answer in terms of so I don't think that explicitly saying my guess is that the ceilings are tall or short helps you with predicting the price, because that guess is inherently uncertain. And so you're better off just having the model do its thing without necessarily having to explicitly output what its guess is for ceiling height. Hope that made sense.
I think I got it. I think I got it. That helped. I got to wrap my head a little bit more around, but I think I got it. Thank you.
All right, cool. All right. I think I'll wrap things up here. Thanks for everybody who stayed. We're a little over time. Once again, next week, Ryan's back in town. So he's going to be doing a presentation on history of OCR up to these days, using very powerful LLMs in order to be able to extract information out of scanned documents. And then in 2 weeks, we'll do another chapter, or depending, we might decide to combine 2 chapters in one, but we'll do the next from the book. And then I think we have one more Saturday in January. So then we'll do a non-book topic. And then the first week in February, we'll do ML news and ML news and other topics. Sorry, I just realized I think I forgot to record this session. Did I? Okay. I just had a heart attack there that I might have forgotten to record it. All right. So hope to see you guys next week for Ryan's cool talk. All right. Thanks everyone. Bye.